Let me mention a bit of history of root of 2. Hippasus, a student of Pythagoras, is said to have been sentenced to death by drowning for proving that the root of 2 is an irrational number. There is no evidence for this legend. However, he is recognized as the discoverer of irrational numbers. We use proof by contradiction, assuming that the roots of 2 are rational numbers. A positive rational number can be written as a divided by b, where both a and b are positive integers and have no common factors. The first method shown here was by Pythagoras. Square both sides, we have. We will shown the equation does not have solution a and b. From this equation, a is even, and b is even too, since for any even number, its square is divisible by 4. This contradicts with that they have no common factors. This is pure arithmetic. The second proof were by Stanley Tenbaum and Joan Conway. Let a be the smallest number so that a square equals to 2b square. In order to show the equation does not have solution a and b. It is equivalent to prove that the area of the two gray squares is not equal to the area of the white square. Look at the two small gray squares in the top right and bottom left corners of the big square. Let the part that covered twice is shown in the dark gray and the part that not covered are shown in white. Since the area of the big square is exactly equals to the total area of the light gray squares, the area of the dark square must the area of two white squares. That is that the square of 2b minus a equals the square of 2a minus b. This contradicts with the assumption that a is the smallest. This is a geometry added algebra method. Now we turn to the third proof. I heard that Timothy Gower showed the method on Twitter a month ago. The key observation in this approach is this positive rational number p over q must not be less than 1 part of q. Because 1 is the smallest positive integer, and the numerator p is a positive integer and cannot be less than 1. It is easy to know that the square root of 2 is greater than 1 and less than 2. So the square root of 2 minus 1 is greater than 0 and less than 1. Since the even power of root 2 is an integer, and the coefficients of the binomial are all integers, so the last equality holds. Therefore the nth power of root 2 minus 1 has a positive lower bound. On the other hand, the fifth inequality implies the nth power of root 2 minus 1 tends to 0. So, there is a contradiction. This is a proof without using divisible. All three approaches are simple and elegant.